Life is incredibly diverse. Have you ever wondered how closely related any two species are? For example, how close is a heron to, say, a duck? And when did their ancestors diverge from each other? Scientists use the molecular clock to figure this out. Let's explore what that is. In all living things, small errors or mutations creep into our DNA sequences at relatively constant rates, kind of like a clock ticking. This is what is referred to as a molecular clock. But how do scientists use this? The clock is first calibrated using known geological events or fossil records. Imagine that we have a group of birds of one species living on an island. Over time, a mountain forms, splitting the birds into an eastern and a western population. The two populations then evolve independently into two separate species, accumulating their own unique mutations and differing genetically by, say, 10%. If we know that the mountain formed 5 million years ago, then we know that the mutations must have accumulated at a rate of 1% per million years in each species. Let's say our western birds have a 6% DNA difference from birds on a neighboring island, where there's a 3% change in each group. Since we know the mutation rate, we can deduce that it's been 3 million years since the two groups separated. Can you compare a mountain gorilla to a bird using the same mutation rate? Good catch. Different organisms often have different mutation rates. Scientists must factor in these differing rates in their calculations to compare. And why do you need a molecular clock? Can't you find lineage data from fossil records alone? Not always. What if the fossil record is incomplete or doesn't exist? One last thing. Can the molecular clock be used to compare human populations? Yes, and that's one of its biggest uses. Imagine a group of humans living long ago. One of them happens to have a unique mutation, shown in blue. One day, he is part of a band that migrates away from the original group. He passes on the blue mutation to his descendants, and over many generations, it becomes widespread in the group. Then, a second mutation, shown in black, shows up in a member of the population, who then migrates to another area. Over time, the blue plus black mutation spread in the new group. Evolutionary biologists can compare the DNA of these groups to determine that the blue plus black group must have descended from the blue group, which in turn came from the original population, and they use the molecular clock to figure out when these migrations happened. The molecular clock is the basis for the study of human ancestry and migration, and is continuously being refined with new data. So if you're wondering how you're related to your friend in Mali cooling in the Sahara, know that we all share a common ancestor, and we can use the molecular clock to figure it out.